Nicely done. Okay, so we were here. So the type of the u minus of r. Type of r is, as we declared here, is expr. Okay. It's expr. Okay, good. And the type of u minus of r, uppercase u minus of r, is expr f parameterized by a being expr. That's different from expr. And to make it back into an expr, we need the int. That kind of wraps it at the value level back into the recursive type that we want to have. So the int is the price you pay for otherwise this nice compositionality that you get. Because what do we get really? Well, do we get much? Well, I would say we get a lot. This brings us, any other questions about the structures before we look at the behaviors? So I think we're okay with the structures, right? What do we get here? Well, now the behaviors become so much simpler than the ones where we had to define, as we were defining these behaviors, we had to worry about multiple things. Here, we worry only about the actual behavior in terms of taking results for children and saying what we need to do with them to get a result for a node. Okay, so to evaluate a plus, given results for the subtrees or children, we just need to add them, or for the minus we subtract them. Or you're familiar with the size and depth, okay? To get the size of any of these composite nodes, we count 1 for the node itself, and we add the sizes of the respective children. Okay, so very good. What are we not worrying about here? That other thing that you would have had to do if you were defining this as an ordinary recursive type. Well, you also have to worry about the traversal. And here we're not worried about the traversal. So it's like when you use fold, these are basically like the arguments to fold. And the fold is the kata. That's the analogy here. So the kata generalizes the fold, and I'll show you the examples where you can see that the kata from Scala mu will work on lists that we define within the Scala mu approach. This separation of the functor from the recursion. Okay, so in your case, instead of L and R, you're going to have a sequence. So how do you add up the items in a sequence? You already know that. Here, and it's not recursive, right? Because it's not recursive at the expr f level, because you're using the operations for sequences. So you're using those. So there's no recursion in these behaviors. And same thing here, the max between those two, that's a simple, a simple if statement or if expression. So these look almost the same. The only difference is you go from a fixed number of children to a variable number of children, meaning a sequence. So any question about the behaviors? Right now it should be pretty straightforward. I'm working on that parser, so let's not worry about that now. The fixtures, anyway, if you define as I mentioned, if you define these factory methods so that they match the definition of your original fixtures should work still, right? They should not require a change. And then the tests, right? So this is where now I take a behavior such as evaluate or size, and with the kata, I apply it recursively. And why does fold for list have 2 arguments? And why does our kata have only one argument, meaning the behavior we're plugging in? I will tell you this is a very simple presentation decision in the following sense. Because in list, because in list you have only two possible situations, right? Either you're looking at an empty list or you're looking at a non-empty list consisting of the head item and the rest of the list. You can say, okay, well, I'm going to write my fold method in such a way that the first argument applies when I'm looking at the empty list, and the second argument applies when I'm looking at a non-empty list. And here, in the general case, I might have 7 different possibilities, so I would have to have a fold method with 7 arguments to express the same, but it's much easier to do branching and to have one argument and then branch on that argument structure. And that's why you're seeing it like this. All right, so any questions, any remaining questions about Project 2B? So everybody, and I have some good news actually. You're going to like this. So is everybody confident now about 2B? Much more than before, right? Okay.
Some of us are a little concerned with bounding box.
Oh, okay, we'll talk about bounding box. Okay, we'll talk about this. Okay.
Yeah.
But so here's the good news that will make you confident, even though you're right now not totally sure about bounding box. So we're going to move this deadline to Monday. Okay. All right. So then you'll have to figure out how this works out with your spring break plans. But at least it gives you the flexibility. So some of you might be going away, so you would have hoped for this not to happen, but some of you might not, and we're all responsible adults, and this way you have a choice of arranging your schedule accordingly. Okay, now back to bounding box. I want you to think of bounding box as being very similar to these things. Okay, so think about bounding box as a more complicated depth behavior, in the sense that you're looking at a group, so you will have, so we agree, bounding box for rectangle is a one-liner. Bounding box for ellipse is a one-liner. Bounding box for location is also a one-liner. Right? Because we do the bounding box for the child and we move it. And that leaves bounding box for group. So, it's like we have only one. There are 5 group-like cases here. We focus on one. And we say, okay, how do we do this? Well, the tricky part is, okay, we gotta have, let's see, how do we express this? Okay. So anyone who wrote their bounding box as a single fold is basically done. Okay, then it's still almost the same code. But, if you didn't, then the way you want to think about this is, okay, so what are you getting as the items in your child sequence for the group node? You're getting the bounding boxes for the children, right? So then, recursively, you're already there where you would be once you return from the recursive invocations. So let's say in your original 2a version, you would say get the bounding box for each child in the group. And here you already get those results as that sequence. So it's just that traversal step that the actual recursive invocation that the catamorphism does for you. Okay. So what are we looking at? We're looking at a bunch of bounding boxes. Okay. And the bounding box thing is compositional in the sense that what are the bounding boxes? The bounding boxes are rectangles. So that reduces the problem to getting the bounding box for a bunch of rectangles at different locations. But that's really what you would have done anyway in your original 2a solution, right? You'd get the bounding boxes, and then you'd get kind of the super bounding box over those rectangles. So that part is still the same algorithmically, but that's what you got to plug into the group branch, right?
The problem we were running into is that it was returning an expert type, and it wasn't letting us cast that as a location.
Yeah.
So to access like X and Y and stuff like that, because expert doesn't have any useful data, then you can't downcast to.
Good question. Yeah, good point. You don't want to. You cannot cast. So that is that is related to the price. Okay, that's a good question. So let's start with this. What is the type of the bounding box algebra? What instead of the int? What do we have? We have the shape without the f. That's right. That's exactly right. That's what complicates things here. So in a way, I didn't tell you the whole story, by giving you these examples. That's right. So, and that's actually something that you're thinking of in the written part also. Okay, how do we do this? Well, let's look at our Scala doc. So this is definitely something I have to tell you explicitly here. So one thing you can do is, what makes the in usable in a case statement or a case expression? What makes the in usable like we are using it here in the first place? Okay, so let's look at the structures. So we can use in like a function. That's because, so see, I'm kind of introducing certain Scala features as we encounter a need for them. So the apply gives us that. The apply makes in look like a function. So it's like anyone knowing C++, it's like the parentheses operator. Okay, so take something of this explicit functor type, and then return something that is an instance of the recursive type. So that's why you cannot, why it's not of type X per F, and you cannot cast it, let's say, to location. You need to unwrap it first. You need to reverse the in. So when you need to take this thing here and convert it back to something where the F is the outermost thing. And then you have, if it has that, it's either a rectangle or a location or those kinds of things. So how do you do that? Well, the unapply makes it possible to use it in a match. Or you could say, you could also use, I think I have another thing that allows you just to access it. Where is that? Okay, I think it might be here. Nope. Let me think. Yeah, the out. That also unwraps it directly. I mean, you could either just invoke out, and it gives you back the thing that has the functor on the outside. So you could take your value s, your shape, and you say s dot out, and that is an instance of shape f over shape. And that one you can do a case distinction on. You can then say, oh, is this a location? Yes, okay, that's the one you expect. So, but you shouldn't really, you shouldn't have to use casting or instance of. It's better to use case expression. That'll get the job done more nicely. Well, this is a really good question. I'm glad you brought this up. That was kind of the missing piece here. Or you could write it like this. Let's see. You could write something like case in S. And then you could say, then you can actually say S match and then case location, for example. Or, even better. What am I doing here? So, because you have a very specific case here. What you're expecting is, and that's the beauty of these case expressions, that you can actually, or the patterns. Right, so in this way you extract everything in one shot. So you don't need to have multiple nested to drill into it, right? You don't need multiple nested match case expressions. You just need a nested pattern. You just do the match on the thing itself, and it's wrapped in an in, so you extract that, and then you drill in further by having just this nested pattern. And this is the structure you're expecting, right? It has to have a bounding box as a location, a rectangle at a location. Does that make sense? Great. So this will solve this remaining problem. Excellent. Any other questions, comments? Great. So, all right. So I will update. Let me update the deadline now. That should be here. Project 2B will make it due on the 3rd, evening of the 3rd. Okay. Well, I think that's reasonable. That should give you some. That should avoid some stress. We don't need unnecessary stress. And then there are a couple of things I wanted to point out. And some of these, of course, will postpone, but I wanted to show you briefly some of the Scala mu code so that you can see that there's very, very little to it. There's no magic here or anything. And, so if you look at the mu ops, that's just this really simple thing where here it's introducing this implicit def, and it's just kind of wrapping it inside this thing, okay, inside this wrapped value around the original value C. So that's part of the Scala Z, the way Scala Z does stuff. So don't pay too much attention to that one. But the one I do want you to take a look at is the mu ops themselves, right? Even though there isn't much to those either, because it just says, well, the catamorphism for for one of our mu thingies is a special case of the catamorphism for the cofree. Just because our mu is a special case of Scala-Z's cofree. So it's consistent with that. But once I show you the catamorphism for the cofree, you will say, oh, that's exactly what we've always seen, basically. So, it's just a little indirect because the catamorphism is a special case of the paramorphism, but the difference is really only this one argument. Okay, so what you're seeing here, you should try to, here you should really try to tie this to your understanding of fold for list. And you remember how fold for list takes two arguments. And here we have only one argument, which is the p. But remember how the second argument of the fold for list, let me show that. Yeah, I gotta wind down here for the presentations. Let's take a really quick look here as anything that we implement as fold, right? So reverse as fold, the thing that we give to the fold takes two arguments. One for the item and one for the partial result. Okay, accumulated so far. So equivalently, we go to the paramorphism. The role of that second argument to the fold is played by P. Okay. And so what I want you to tie this to, because I don't have an implementation of fold at my fingertips right now, but what I want you to tie this to is the group branch of any of your 2A behaviors. What does the group branch do? It says recursively apply the behavior to the children, right? What method does it use to apply the behavior to each child? How does it apply the behavior, because there are multiple children, 0 or more, how does it apply this behavior that we're defining recursively to each child? Map. That's right. And why did the map work? Because the children happen to be a sequence on which we have map, right? So this is just a generalization where we say, well, it doesn't necessarily have to be a sequence specifically. It could be something more general as long as it has a map. That's the functor requirement, okay? And once we have the functor, once we say, well, we have nodes whose children are given by a functor, we have this map. So we take the tail in a more general sense than list. So this is the item in the node, whatever value is stored in the node, which in our mu-based thing we don't have. So in the catamorphism we don't have this, and in mu we don't have this either. Okay, so we only have that. And that's what your 2A manually implemented recursive behaviors look like. So you take the children of the current node, which is what tail stands for here, and you map the behavior that you're about to define recursively to the children. And the behavior we're defining here is para applied to P. So we're mapping para applied to P to the children. So this is simply or you could think of what you wrote earlier as an instantiation of this code, this very piece of code, in the sense that, well, we're doing away with making the node itself, the node's children available to P. So that's what distinguishes the paramorphism from the catamorphism. Don't worry about that. And then we don't have any stuff really stored in the nodes other than the children. And then for that part, to apply the behavior to the children, we take the children, we assume that that this structure containing the multiple, possibly, children supports map. So by saying it has to be a functor, we know that it supports map. And then para with argument P is the behavior we're defining here. Para with argument P. Okay. So we're not passing a modified argument function. So in that sense, it's just like when we say depth. Depth you could think of as paramorphism or catamorphism applied to your non-recursive depth behavior. And then it's the same thing here. So, but the key point is that we formed the recursion over the functor, and that guaranteed us that we could apply the behavior, we could push the behavior into the structure by using the appropriate map method available for the children of any node. Okay. Any questions, comments? Okay, great. So, yeah, it's going to take time to sink in. You know, as I mentioned, it took me. So, you know, my little journey. You know, so I worked on programming languages for my thesis, and that was a long time ago. That was starting in the late '80s, and I finished in '92. And then I became much more applied, looking more at object-oriented programming, at distributed systems, and so on. And then since I started teaching the programming languages course again about 4 years ago, I became obsessed with these algebraic approaches. And what you're seeing is a point in my own journey where I finally made sense of this, and I was able to articulate it in the form of this small library. You know, so that's basically the effort I had to put in to this to make sense of it for myself personally. So, you know, it's going to take, I'm hoping by having done this, it's going to reduce the barrier for you to get to a point where you have a working intuition dramatically. But it does take time and practice. So, you know, don't expect to make full sense of all of this overnight or anything, but by doing this project, I think it'll get you gradually to the point where you have a working intuition. Okay, so, you know, I really appreciate your effort in working on these things in the context of this course, and I'm hoping that it'll add to a dimension of your efforts as a computer scientist or software engineer, you know, that one might otherwise not actually acquire when doing things the conventional way. You know, so my hope is that by embracing these algebraic methods, one will actually be able to discover and articulate abstractions that one might otherwise not see. And then, as you saw here, we got to a point where for any recursive type based on a functor, we get by with a single implementation of the recursive behavior. Okay, and we just need to parameterize it with these fairly simple non-recursive case distinctions. So from a software engineering point of view, I would argue that that's valuable. But then we're out of time for now. We got to transition to the presentations, but we'll pick it up from here next time. I'll wrap up a few things, and then we'll start moving on to the next major topic, which is representing and interpreting programs in a programming language. So in other words, we're going to do some similar things, but we're going to we're going to use similar techniques, but we're going to apply them to trees that represent, instead of expressions and shapes, to represent more interesting programs. So the expression example is, of course, a step in that direction, because we just need to add a few other constructs to the expressions, and then we'll have programs with expressions being embedded in the programs. All right, any questions, comments? Very good, so I'm going to wrap up the recording.